All right, hello everyone. Thank you all for coming back again. Today we have Tài Huy from Tulane University and is going to tell us about Newton-Okounkov bodies, Rees algebras, and analytic spread of graded families of monomial ideals.
All right, thank Eloisa for the introduction, and thank you the organizers for organizing this awesome event and providing me this opportunity to speak. So today I'm going to talk about the connection between commutative algebra objects, which is graded family of ideals, in particular monomial ideals, and convex geometric objects. So this is based on our recent joint work with my advisor, Thái Hà. So as I mentioned, the kind of a broad problem that motivated this projects is we want to investigate the connection between algebraic properties and invariants of graded family of ideals, which I will define later, and geometric properties and invariants of some associated convex body. So in particular, in this project, we look at the graded families of monomial ideals, because for monomial ideals, there is a very natural and well-known way to associate a monomial ideal and a polyhedron geometric body. So we will use combinatorial data from a convex bodies, the so-called the Newton-Okounkov body, to first characterize the Noetherian properties of the Rees algebra of the graded family. And then in terms of algebraic invariance, we will give a combinatorial interpretation for the analytic spread of a graded family, and then focus on symbolic powers, because that's my main theme of study. We will give combinatorial bounds for symbolic generation type and the so-called standard Veronese degree. So that's the outline of my talk. So some notation and terminology during my talk. R will be the polynomial ring over a field in n variables, and the special M is the maximal, the homogeneous maximal ideal. Then if we have a collection of ideals in the ring R indexed by the natural number, then we call it a graded family or a graded system if those ideals satisfy this graded condition, which means that I sub p times I sub q will sit inside I sub p plus q for all p and q. So the graded family, the terminology graded, and the graded system, the graded condition suggests us that we can make a graded algebra out of this graded family. And by taking, so we define the Rees algebra of this graded family by taking the direct sum of all of the ideal, taking account the degree given by the indexes of the ideal. So this is a graded algebra because of the graded condition. So then to this Rees algebra, the graded algebra or the graded family, we can associate to the Rees algebra a convex body. Well, and it turns out to be the Newton-Okounkov body in some special and very important cases. So this defined by, so when we have a monomial ideal, for each monomial, we take the exponent vector, which give us a point in the real vector space in n-dimensional. And then we divide it by the index or the degree component in the Rees algebra of the ideal. Then we have a point. So we collect all of those points, and then we take the closure. So this is just the Euclidean closure. Then we have a set that is our definition of the Newton-Okounkov body, associate to a graded family of monomial ideals, I sub k. So let me talk a bit briefly about the history about this Newton-Okounkov body. So the term Newton-Okounkov was dedicated to Okounkov pioneering work on multiplicity of algebraic varieties, and then is systematically developed by Lazarsfeld and Mustata in more geometric setup, and independently by Kavak and Kubansky in more combinatorial setup. And in the earlier work is usually defined for a graded algebra of integral type. so that we have a bounded Newton-Okounkov body. So they can talk about the volume, or define for a great family of m primary ideals, where we have, the complement of the Newton-Okounkov body will be a bounded body. So we can again talk about the volume. But here in our definition, we don't require any integral type of the algebra or the m primary ideal. So you can see that our Newton-Okounkov body is unbounded, and the complement is also unbounded. Because we look at other things rather than the volume. All right, so this is some special cases, and it's actually some important cases. So if we look at the graded family of all ordinary powers of a monomial ideal, it turns out that the Newton-Okounkov body coincides to the so-called Newton polyhedron of the monomial ideal I. And the definition is we just take the convex whole of all exponent vectors inside the ideal I. The second important example, special case, if we look at the family of all symbolic powers of a monomial ideals, this coincides to so-called symbolic polyhedron first introduced in the work of Cooper, Ambray, Ha, and Hoffield, when they used the symbolic polyhedron to study the containment problem and the velocity constant of a monomial ideal. And this is the precise definition of the symbolic polyhedron. So we take, it begins with a primary decomposition of the ideal I, and then we calculate some Newton polyhedra of the primary ideals. Then we take, intersection. So you can see from the definition is kind of complicated compared to how we calculate the Newton polyhedron. But it turns out that at least for square-free monomial ideals, the symbolic polyhedron is easier to calculate, in the sense that because for polyhedron in general, there are two ways of represent a polyhedra. First way is by represented by the intersection of all half space, defining half spaces. And the second way is to represent by the Minkowski sum of the convex of a polytope and a recession cone. So for a square-free monomial ideals, if we can write down the primary decomposition of the ideal, then it's easier to find the defining hyperplane of the symbolic polyhedron of I. So here, if I have this concrete example, and I look at the primary decomposition, which is just prime ideals, then this prime ideal would give me one defining hyperplane of the symbolic polyhedron, which is x plus y equals 1. So here in the picture on the left, the symbolic polyhedron of I has 6 defining hyperplane. 3 of them will be the coordinate hyperplanes, and the other 3 come from the primary decomposition. So this is just the hyperplane y plus z equals 1. This is just x plus z equals 1, and this is x plus y equals 1. So on the other hand, to calculate the Newton polyhedron of I, actually we have to take the convex whole of these 3 points, actually these 3 red points, which are the exponent of the minimal generators of I, which is 1, 1, 0, 0, 1, 1, and 1, 0, 1. And then we take the convex whole of that, and we Minkowski sum with the recession cone, which all the time being the positive often. So look at these two. So in terms of Newton polyhedron, it's actually more complicated to calculate the defining hyperplane, and it turns out to be kind of a problem in a lot of questions. So in the Newton polyhedron, besides 6 defining hyperplane of the symbolic polyhedron, we only have an extra defining hyperplane here, which passes through these 3 vertices. Here we don't have that because we have an extra vertex, which is the middle red point in here. It is not an integral point, and it is a rational point of coordinate 1/2, 1/2, 1/2. And this picture actually revealed the fact, the algebraic fact that for this ideal, the symbolic powers and ordinary powers are not equal. And of course, when we look at the pictures, you will see later, we can tell more about symbolic powers and ordinary power of the ideal I. So a quick remark here is that, so it's not very hard to see that we can show that the Newton-Okounkov body turned out to be the closure of the union of all Newton polyhedron of each ideal in the great family divided by the index K. And so if we just look at the thing under the closure, it is kind of recently named and investigated by the work of Camarnero and many other authors when they call this a limiting body of the greater family. Actually, the same asymptotic objects were also studied long ago by Mustada, Wolf, and Mays in different contexts. So now I want to move on to the first question in our project. We want to characterize the Noetherian properties. So first, why? Why is the Noetherian properties? Well, I would say first, like, it's very natural question, right? If you give me any algebra, maybe one of the first questions that I ask myself is if it's finally generated or not, right? And also, it's actually the problem of determining if the Rees algebra is Noetherian or not is very difficult in general. And there's many, like a lot of examples show that for family of even symbolic powers of an ideal doesn't give you a Noetherian Rees algebra. On the other hand, the symbolic Rees algebra of a monomial ideal is shown to be Noetherian. So for monomial, we know that for family of symbolic powers of monomial ideals, the Rees algebra is Noetherian. So in this project, we focus on the Rees algebra of a greater family of monomial ideals. So this is our first observation. So if we have two greater families of monomial ideals which have same integral closure, then the Newton-Okounkov body of them are the same. So this is just a first observation, but it's also show us kind of a limitation of this method. So somehow the Newton-Okounkov body doesn't distinguish between two greater family with the same integral closure. So, but it also suggests us something about, if we want to investigate something, maybe we want to start with something that preserved under the integral closure operation. So that will come later with the analytic spread. Well, but this is the first theorem. So we used to characterize the Noetherian property of the Rees algebra. So if we have a greater family of monomial ideals, then the Rees algebra, then the following equivalent, the Rees algebra is Noetherian. The Rees algebra of the integral closure is Noetherian. The limiting body is a polyhedron, and by polyhedron, I mean rational polyhedron. And in this case, it's very easy to calculate the Newton-Okounkov body because it turns out to be the Newton polyhedron of some ideal inside the greater family divided by the index. So that's completely characterized the Noetherian properties of the Rees algebra based on the polyhedron property of the limiting body. Right, so let's look at some example. And I would say that we know how to calculate this number C concretely. And for square-free monomial ideals, or for some kind of more generalized classes of square-free monomial ideals, we know how to find the least possible number C. It's just that we have the formula for the fourth condition in the theorem. So we can look back to this theorem, this picture, this example. So we saw later that this is the symbolic polyhedron with the 4 vertices, and this in the middle is not integral vertex. It is the rational but not integral. So imagine that we just scale everything by 2. In the sense that we multiply everything by 2. So these 4 vertices become integral vertices. So this becomes the vertex 1, 1, 1. So that would give you a Newton polyhedron of some monomial ideals. And it's not hard to see so if you scale everything by 2, it is the Newton polyhedron of the second symbolic powers of I. So the number C in the theorem is 2. Because for symbolic powers, right, the Newton-Okounkov body is the symbolic polyhedron. So actually, these 2 pictures are on pictures of all Newton polyhedron of this is the even symbolic powers of I, where this is on the picture of Newton polyhedron of odd order symbolic powers of I. So actually, this tells you about the on of the Newton polyhedra of each ideal inside your graded family of symbolic powers of I. Well, but this is my favorite kind of example, but it's also kind of a misleading example in the sense that it shows you very like simple geometric thing, but in general is really complicated to calculate a Newton polyhedron, not talking about the symbolic polyhedron. So in fact, we have some other big kind of example where if you take just an edge ideal of a cone over a 5 cycle, the symbolic polyhedron turns out to have 17 vertices, and the number C in our theorem turns out to be 30, which is the least common multiple of all denominators of all vertices, and we can show that this is C equals 30 is the least possible integer since that this happened. Right. So another example, this is kind of not a concrete example, but it's kind of give us a way to like construct a lot of graded family that has Noetherian Rees algebra. So if we so this is the definition of the so-called R real power of monomial ideals. So this is defined by taking on monomials. So it's actually generated by on monomials, such that the exponent is inside R times the Newton polyhedron of I and on the integral point inside that body. So that's the R real power. And when the number I is a rational number, it's just the usual fractional power of an ideal. And we start with this, and if we look at some function, some real value function, with positive real value function, which is subadditive in the sense that it's satisfying this condition for on M and N, then this limit always exists because of the subadditive properties of the function. But here we suppose that this limit is a rational number. And furthermore, it's attained at some value k0. Then if we consider this kind of graded family, given by the real power of fk, real power fk of I, then this is a graded family. And the point is we can calculate it's not hard to calculate the limiting body. Turns out to be some multiple of the Newton polyhedron of I, which is a rational polyhedron. So by our theorem, we can conclude that the Rees algebra in Noetherian algebra. So this gives you a lot of like graded family, which has Noetherian Rees algebra. So you can pick like some subadditive here, and example for subadditive is a lot. And sometimes you can choose some like really crazy subadditive function. Right. So remember that we characterize the Noetherian properties in terms of polyhedron properties of the limiting body. Well, you may ask, how about the polyhedron of properties of Newton-Okounkov body? Turns out to be no. We can have very simple example like this, where the Newton-Okounkov body turns out to be rational polyhedron. So this in the pictures is blue region included the red segment. So this is a rational polyhedron where the limiting body is only the blue region without the red segment. So in this case, although we have a rational polyhedral Newton-Okounkov body, our Rees algebra is not Noetherian. So this is the best that we can see from the Newton-Okounkov body in terms of Noetherian property. And in fact, in general, if we just pick any random graded family, it's very likely that we will end up having a non-polyhedral Newton-Okounkov body. So as a remark here, actually, we can start with any closed convex set that absorbing the positive ortho. That is, if we just do the Minkowski sum of the convex set and the positive ortho, we have everything sit inside the convex set again. Then from that convex set, we can construct a graded family of monomial ideals that have the Newton-Okounkov body being that convex set. So it's very likely if we just start with some random graded family and we have something not even polyhedron. Well, okay, so now I want to talk about algebraic invariant. So first, let me just briefly survey some of the result in this theme. So maybe the first and the kind of most celebrated result in this kind of theme of work is the formula multiplicity equal volume, which show here. So if we have a graded family of monomial ideals, then the multiplicity of the graded family, which defined like this, then it's n factorial, the limit of the dimension or the length of this quotient ring divided by k to the n. It turns out to be n factorial times the co-volume, which is the volume of the complement of the Newton-Okounkov body associated to that graded family. Of course, this formula can be generalized in, in really generalized sense for graded system of graded family of other ideals in local rings, and in other direction in multiplicity for and mixed multiplicity and mixed volume of certain Newton-Okounkov body. And it's due to Mustata and Kalbeck and Kowalski. So the other work on this subject is the study containment of a monomial ideals through the symbolic polyhedron in the work by Cooper and many others. So in this work, they actually study the containment problem between symbolic powers and ordinary powers of monomial ideal through the symbolic polyhedron. They also study the Wonsby constant through the combinatorial data in the symbolic polyhedron of the monomial ideal. Also talking about the related work in terms of containment problem, one can talk about the numerical value related to the containment problem, which is the so-called asymptotic resultant numbers. It also can be studied for monomial ideals, can be studied through the skew valuation on the Newton polyhedron by the work of de Pascal and other authors. And the Wonsby constant for a graded family, which I'm very interested in the Wonsby constant, is defined by the limit of the minimal degree of generators of each ideal in the graded family divided by k. And it turns out that this Wonsby constant in the context of monomial ideals can be computed by looking at the combinatorial data on the points in the Newton-Okounkov body in the work of Camanero and many others. Right. So these are just a brief survey for the work on algebraic invariants of the graded families of ideal through the combinatorial data of the Newton-Okounkov body. Our work focus on another algebraic invariant, which is the analytic spread. So this is the definition. So if we have a graded family of monomial ideals, or ideals in general, we can define the analytic spread as the crude dimension of some sort of a kind of special fiber ring of the Rees algebra. So something about this invariant. So in the recent work, Petkowski and Saka show that if I is a filtration, in the sense that if we have in the family, if I sub k plus 1 is contained in I sub k for every k, then this number exists. And furthermore, it's bounded above by the dimension of the ring. So it's very similar to the inequality of the usual analytic spread that we know. In fact, it turns out that if we use the same technique with some modification, we can extend the result to any graded family of ideals. So that's still true for any graded family of ideals. And we can also improve the bound, the above bound, the upper bound, by looking at just take the maximum of the analytic spread of all the ideal inside the graded family. In fact, we can do a little bit more, but this assures that this analytic spread exists. So some terminology, if we look at the honorary power family or symbolic power family, and we use the usual analytic spread terminology, or we use the symbolic analytic spread for I instead of analytic spread of the grade family. Okay, so as I said, we want to give a combinatorial interpretation of the number of the analytic spread, and that will be through the maximum dimension of a compact phase in the polyhedron. So we denote MDC of P is maximum dimension of the compact phase of the polyhedron P. And so this is the theorem. But we need I to be a Noetherian graded family of monomial ideals. If that's the case, then the analytic spread of the graded family can be computed by look at the maximum dimension of compact phase of the Newton polyhedron, Newton-Okounkov body of the graded family plus 1. So this gives a combinatorial formula for the analytic spread. So the question here is kind of, we have to require the Noetherianness, the Noetherian properties of the graded family. This is still true if we don't have that. Instead, we only have the polyhedral properties of the Newton-Okounkov body. That's the question, and we don't know the answer yet. So I've done some very limited calculation, and it's also it always suggests that that should be the case. So some corollaries, if we have two graded families that we share the same integral closure, then the analytic spreads of them are the same, right? This is just a direct corollary because we know that the Newton-Okounkov body of them are the same. The second corollary is that first, if we strict ourselves to the ordinary family, then we recover the earlier result by Bivia Alsina. It says that the analytic spread of a monomial ideal is equal to the maximum dimension of compact phase of the Newton polyhedron of I plus 1. The other very interesting corollary is I know some people are interested in this invariant. That is the symbolic analytic spread can be computed by look at the symbolic polyhedron. So this is very nice, right? Because so we don't have a way to like calculate the symbolic analytic spread in general yet. But we know at least like at least for monomial ideals, we can use Macaulay tool to calculate the symbolic polyhedron, and we can calculate all of the compact phase and the dimension. That would give us the symbolic analytic spread, right? Right. So let's look at some more example. So again, let's visit my favorite example. So this is the symbolic polyhedron, and this is Newton polyhedron. So in this picture, so we see there are only 3 compact faces, right? Which is the 3 segments that pass it through that join these two and these 2 vertices, right? So we only have 3 compact faces, and each compact face has dimension 1. So it shows that the symbolic analytic spread of the ideal I is 2. Whereas in this case, because we have an extra compact face, extra defining hyperplane will give us an extra high compact face. So in this Newton polyhedron of I, the compact face, the maximum dimension of compact face 2. So the analytic spread of the ideal I is 3. Right. So now I want to just mention a bit about the other pattern definition of the analytic spread of the great family. So we can define an invariant L star of I is the minimum of all number T such that, so mu here is the number of minimal generators of ideal I, okay? So this is defined as the minimum number of T such that the number of generators, the minimum number of generators of IK grow like a polynomial in degree T minus 1. So what is the point of defining this, use this definition? And actually this is used by Hailong and Montano in their work on symbolic analytic spread. They actually use this definition as the definition of a spread of the family. Well, it turns out if I is Noetherian, then L star of I is L of I, right? By Hilbert polynomial theorem. But it's not known in general if this number is always finite. And as I mentioned, this number has been investigated by various other, including Hailong Dao and Jonathan Montano and Hoa Kimura Terai Trung. One reason that we want to look at this this number and to see if we can tell something about this number based on the combinatorial data of the convex body is that if we look at this mu of IK, it's actually count the number of integral points in some sense. And if we think of it that way, then the number L star of I measures some growth rate of the number of integral points in our convex body. And it's very interesting to know if there's a connection between that growth and some combinatorial data, as we predicted or we hoped that is related to the maximum dimension of compact phase. And if it's either case, then at least in Noetherian, we recover our earlier result. So I just want to mention an example for this invariant. So if we take a graded family of m primary and full monomial ideals, for example, if we take integrally closed monomial ideals, and suppose the Newton-Okounkov body is a rational polyhedron, then it turns out that this number turns out to be the dimension of R, which is what we expect it to be. Because for m primary ideals, right, the analytic spread of each of them will be the dimension of the ring. And so if we think of the analytic spread for that graded family, we should expect it to be the dimension of the ring, right? And it turns out that the L star, at least the L star of that graded family, is the dimension of R. And we don't know yet if the analytic spread Li is the dimension of R, but at least we know that this L star. Right, so now that's for the analytic spread of a graded family of monomial ideals in general. Now we focus back on the family of symbolic powers of a monomial ideal, and we focus on the so-called generation type and the standard Veronese degree of the symbolic Rees algebra. So first, let me state this fact. So if the symbolic Rees algebra is finitely generated, it's equivalent that we have some number d such that the dk symbolic powers is the k honorary power of the d symbolic power. So in other words, this symbolic Rees algebra is finally generated if and only if the d Veronese subalgebra of the symbolic Rees algebra is standard graded, right? And the first invariant that we look at is so-called the standard Veronese degree, which is the list D such that the D Veronese subalgebra of the symbolic Rees algebra is standard graded. And we're interested in to calculate that at a degree. But we can only bound that number, and this is the theorem. So if I be a square-free monomial ideals or some kind of generalized version of square-free monomial ideals, and suppose we know all the vertices of the symbolic polyhedron, if we take C to be the least common multiple of all denominators appearing in all coordinates of all the vertices, then C is the lower bound for the standard Veronese degree, where the upper bound given by C multiplied with this number for the maximum dimension of compact face of the symbolic polyhedron. And so these two bounds are sharp. So in the sense that we have example, it's not complicated example to show that this, yeah, of course, the upper bound is quite obvious to see, like there's example for it to be sharp, because if we take any monomial ideal such that the C, the ordinary powers and symbolic powers are the same, then C and the standard Veronese are the same and is one, right? So, and the other upper bound is also sharp, and there's not too complicated examples to show that it's sharp. The other invariant that we look at is the so-called symbolic generation type of the ideal I, which is just defined as the maximum algebra, like degree of algebra generators of the symbolic Rees algebra. So it's defined, this is the precise definition, and this is our theorem. So if we have a square-free monomial ideals or some kind of generalized version of square-free monomial ideal, and if we know all the vertices of the symbolic polyhedron. Now we take di to be the least common multiple of denominator of coordinate of each vi. And we take the capital D to be the maximum of all di. Then if d is greater than or equal to 2, the standard, the symbolic generation type is bounded above by this number. So it's already is involved all of the, everything inside here are just combinatorial data from the symbolic polyhedron. If d equals 1, then we have kind of a slightly tighter bound compared to the d greater than or equal to 2. And in the second bound, actually is sharp. So we have it's a little bit more complicated example, but we have example for this to be equality. For the first bound, we don't know if it's sharp or not, but is actually an improvement of earlier result on the degree the bound for symbolic generation type. And that's all I have for this talk. And thank you for listening. And yeah.
Great. Thank you. Let's thank Thái.
Thanks.
Questions for Thái? Okay, so you were just telling us, could you go back to the bounds you were just showing us?
Yeah.
So you said you don't know if this first bound is sharp.
Right, that's right.
Right, okay.
Yeah.
Do you have any examples that get close to it? I don't know what I mean by close.
Yeah, right. So I don't even have like, it's really close, like difference by 1 or 2. No, yeah.
Okay.
Yeah. So the best bound that we know of, right, is the bound from the work of Herzog, PB, and Trump, when they bound by determinant of a lot of things there.
Mm-hmm.
So yeah, so this actually improves that a bit in the sense that to get to the bound in N only, we still need some determinant and such, but because of the fact that we just multiply by this and it's less than the dimension of the ring, which is N, so we have an improvement to that bound. That's never, I don't think that the bound for the determinants never be a good bound because it's exponent bound.
Mm-hmm. It's also really hard to compute with the standard generating degree sorry, the standard generation type is.
Yeah.
Anyways, and can you show me again the bound from the previous slide also?
Yeah.
Is this the one I mean? Yes, it is the one I mean. You were here pointed out that you do know the upper one is sharp. Is that what you said?
Yeah. Yeah, and it's not complicated at all.
So what's an example?
What?
So what's a good example?
So we just take the xy and intersect yz, but with some power, because this theorem works for square-free monomial ideals, but also work for the intersection of all powers of prime ideals. Okay. Yeah, a lot of things that I mentioned here work for that. We call it like linear powers of linear type or something. But it's just intersection.
Say again what that means? The intersection of?
Yeah, the intersection of power of prime ideals, monomial ideals. So it's like xy to the 2 intersect yz to the 3 and so on. Yeah.
Mm-hmm. Great, thanks.
Yeah.
Does anybody else have any other questions they want to ask? All right, if not, let's thank Thái again.
Thank you.
Thank you, Thái.